Hello, in this module we will introduce the Gaussian random variable and the corresponding PDF. A Gaussian random variable is also called a normal random variable. It is one of the most important random variables as many physical phenomena can be modeled readily in terms of a Gaussian PDF. For instance, the thermal noise, which is always present at the front end of a communication receiver, is modeled as a Gaussian random process whose samples are Gaussian random variables. In this module, we will understand the Gaussian PDF and the CDF, and we will discuss the importance of the Gaussian PDF. To begin with, let us first understand how to denote a Gaussian random variable mathematically. Okay, so let x be a Gaussian or normal random variable. In short, we write GRV with mean, mu and variance sigma squared. This is mathematically denoted as, that is, x is distributed as per Gaussian distribution or normal distribution with mean, mu and variance sigma squared. So, this is how it is written mathematically. Let us note clearly, this x denotes the random variable. This symbol is used to show the distribution. So, distributed as normally. This script n is used to denote the normal distribution. Mu denotes the mean and sigma square denotes the variance. The sigma, which is the square root of the variance, is the standard deviation. A Gaussian random variable is characterized in terms of its probability density function PDF as follows: lowercase f subscript capital X of a small x, that shows the PDF, and it is given by 1 by root 2 pi sigma square into e to the power minus x minus mu whole squared upon 2 sigma squared, where x can lie in the range from minus infinity to plus infinity. This is a very important distribution, and therefore this expression must be memorized. Pictorially, it looks like a bell-shaped curve as shown here. Something like this. So, there is the zero line. The peak occurs at the mean value mu, where the value of the PDF fxx is 1 over root 2 pi sigma squared. At a distance sigma from mu on either side, mu minus sigma and at mu plus sigma the value of the PDF is 0.607 upon root 2 pi sigma squared. These are the points of maximum absolute slope on the PDF curve. This distance is 2 sigma, sigma being the standard deviation is a measure of the spread of the PDF around the mean. It can be shown that the mean of the Gaussian PDF is indeed mu as per definition, that is the mean expectation of x, which is defined as integration minus infinity to infinity x fx x dx is indeed equal to mu, and the variance, so let me just write mean, and the variance of x, which is given by expectation of x minus mu whole squared, which is integration minus infinity to plus infinity x minus mu whole squared fx x dx, and that is equal to sigma squared. So, in a separate module we will prove these expressions. The CDF, the cumulative distribution function for a Gaussian random variable, is given as follows: capital F subscript capital X of a small x. Okay, so fx x equal to integration minus infinity to x 1 over root 2 pi sigma squared into e to the power minus some dummy variable tau minus mu whole square upon 2 sigma squared d tau. Recall that the CDF is related to PDF as follows: integration minus infinity to infinity minus infinity to x fx tau d tau. This CDF, when sketched, looks something like this. This is x, this is say the 0 line, the at mu, when x is equal to mu, the CDF has a value of 0.5 because it amounts to integrating this curve from minus infinity up to mu, which is half of the total area of the PDF curve, and the total area of the PDF curve is 1, so its half is 0.5. When x tends to infinity, it tends to 1, which it should, because the maximum value of CDF is 1. At x minus, at mu minus sigma, the value is 0.159, and at mu plus sigma, the value of the CDF is 0.841. Note that the CDF of a Gaussian random variable is continuous reinforcing that the Gaussian random variable is a continuous random variable. Let us now look at some of the attributes of a Gaussian random variable which makes it important. So, why is a Gaussian random variable important? So, number one, it's a good model for many physical phenomena due to a well known relation from mathematics called central limit theorem. The central limit theorem states that the distribution of a large number of independent and identically distributed random variables combinedly is Gaussian. We will formally look at the central limit theorem in a separate module, but broadly it states that the sum of a large number of independent and identically distributed random variables. By the way, independent and identically distributed is frequently written as IID. The sum of a large number of IID random variables is Gaussian. We will look at the mathematical form separately, but it may be noted that many physical phenomena which are random in nature can be thought of as the result of a large number of identical and independent random events, and therefore the distribution is Gaussian. A classic example from communications engineering is the thermal noise. Another important feature of Gaussian random variables is that they are easy to analyze. The reason being, the Gaussian random variables are characterized completely in terms of their first two moments only, namely the mean and the mean square value, or equivalently the variance. And because of that, the mathematical construct that we obtain for analyzing a Gaussian phenomenon is of second order, which is tractable mathematically. Another important feature of a Gaussian distribution is that the linear combination of Gaussian random variables is also Gaussian. That means, if say x1, x2, xn are Gaussian, then some random variable y, which is ax1 plus a1x1 plus a2x2 and so on plus anxn, is also Gaussian with some mean and variance that may be computed. In other words, we can say that the linear transformation preserves Gaussianity. Another very important feature of a Gaussian random variable is that many other PDFs of practical importance are related to Gaussian PDF and they can be derived from it. For instance, suppose x1 and x2 are Gaussian random variables, then some other random variable y, which is defined as the square root of x1 square plus x2 square, then y can be shown to have a Rayleigh distribution, and is very important in modeling feeding in a wireless communication system. There are many other such PDFs which can be derived from Gaussian PDF. Yet another important feature of a Gaussian random variable or a Gaussian PDF is that it can be used to represent an impulse function, a Dirac delta function. We know that an impulse function is equal to 0 for x not equal to 0, and when it is integrated from minus infinity to infinity, it yields 1. A PDF also possesses this property that its area is unity. When we look at the Gaussian PDF, let us look at pictorially. It looks like a bell-shaped curve, and the spread of this curve depends on the sigma. If sigma is made very small, for instance, it somewhat looks like an impulse. So, in the limits as sigma tends to 0, the PDF of a Gaussian random variable can be used to represent a Dirac delta function. Specifically, it can be written as mathematically delta x minus mu equal to 1 over root 2 pi sigma squared exponential minus x minus mu whole square upon 2 sigma square in the limits as sigma tends to 0. So, there is an impulse occurring at x equal to mu. The advantage of this representation is that it is infinitely differentiable. It is a smooth function and therefore infinitely differentiable. So, in this module, we looked at one of the most important continuous random variables, namely the Gaussian random variable and the corresponding density and distribution functions. We also discussed some of the key features of Gaussian random variable which makes it important. So, that is all for this module. Thank you.